Hello everyone, welcome back to our class. We stopped at just writing the outline of conservation of momentum, the equation for conservation of momentum last time. So, we will start from there. Hopefully, we will derive conservation of momentum and conservation of energy before end of today's class, and probably go a little more beyond that. So, when we said conservation of momentum, we said time rate of momentum rate of increase in volume V is equal to minus of net outflux across the surface S plus the net force acting on the volume V. Okay. If I say that there is no outflux, then I will say that the net force is going to be directly increasing the net momentum at some particular rate. That is your second law of Newton's second law, right? Just directly gets you that. This is the extra term which is the loss term from the volume. So, keep it this way. From in a simple expression we will write for rate of change plus all the remaining forces. Now, we could have so many forces possible. So, we will just write it as the stress tensor stress tensor is the full matrix form of it, 3 by 3 form of it, and that is going to include along the diagonal it will be the normal force components, and the off diagonal terms will be your shear stress terms, right. You know tau x y, the most common one used in Newton's law of viscosity, like that. Okay. So, this is the full equation. I am going to say that this F B is your body force term, that is if there is any say magnetic field across, and that is going to cause some bulk force or gravitational force. Okay. This is all force per unit volume, the way I have written it. Okay. No, it is actually absolute force, it is no per unit volume or anything, it is just absolute force, no per volume mass of no. Now, we will say we will start simplifying this, and I will say this is going to be equal to 0 in most of my problems. In gas dynamics we will mostly say there is no gravitational field or any other body forces, electric or magnetic field, we do not have any of that, and this we will simplify a little further. Now, I will write this whole term by splitting this into diagonal term and off diagonal term. I will keep only the diagonal term part, am writing it as tau shear, which means I am having all the diagonal components of this 0, and then I am taking, oh, I have to take a dot product with this, dot product with the perpendicular vector from there, surface vector, and this is the force is acting along the n direction, normal force. If there is a surface and the pressure is acting from outside onto it, the normal is going to be out of the box and pressure is going to be inward. So, that is giving you this minus sign in there, okay. And then in shear force it will automatically take care of the sign based on this dot, okay. It will take care of it by itself. Now, we substitute these two inside here, and we are going to say in our simple gas dynamics world we will neglect this. We will say there is no shear force, as in we are going to consider inviscid flow problem as of now. Of course, we will come back and say friction can be taken into account at a later stage. As of now we will say there is no friction, there is no shear forces inside my flow. So, we will neglect it for now, only normal force component will be there, okay. So, now I just have to substitute all this inside. Of course, I can just take this, I want to convert all of them to volume term, volume integral term. So, this is going to be del p not del dot p. That is just gradient of scalar, pressure is a scalar field. So, gradient of that is a vector, and that is your force direction. We just got to this form, that is just one term, we still have other terms. We want to look at the next term, the advection term. This term, when we want to convert to the volume integral, it is not very easy. So, we will write a vector identity below this and go by parallel, that is easier for us. So, this is a vector identity, we just take it from mathematicians, we will just use it. If you look at it, really it is just differentiation by parts, that is all we are doing inside this, it is nothing great, okay. Differentiation by chain rule, I guess that is what it is called, we are just doing that inside here, it just looks very complex. Of course, we still do not know what to do with this term, we will go back to that and write another identity for that. If you are using tensor notation as in the Einstein notation, index notation, then this life will become a little easier. I just do not want to teach you this in this course. So, we will just live with vector notation and just get over with it. We will just use it only once in this whole course, and that is this point, we will not worry about it too much. So, now I have to just see the parallel between this and this. My b vector is a velocity vector, a vector is another velocity vector, this phi is a scalar, and that is my density in this case. Now, I just have to go and find the parallel and write the equation, that will become So, I used this to get to this form. Okay. So, now we can simplify it a little bit, just pardon me to change this to flower bracket. Now it is consistent. Okay. Now this looks simple enough to work with. I still want to think about this term. It is not very easy to work with. So we will go and simplify that a little more. Again we will go and ask mathematicians. They will tell me another identity for it. So we will go to this place and start writing from the beginning. I will pick the identity right now. This is an identity of just the operator operating on a scalar multiplied by a vector. That is what this is. Okay, it is a dot del as an operator, differentiation operator, acting on the product of a scalar and a vector. That comes out to be this. Okay. So now we just have to look at it in terms of our rows and u's. We had an expression that was this. Now this can be written as this form. Remember that here this is not integral over surface to integral over volume, that is not what we did here. This is just expressing this in terms of this whole expression. If you go back and look at where it was sitting here inside this volume integral, that is still here inside the volume integral. So now I have to take that expression, substitute inside here along with this expression, that will be 3 terms inside this. All the 3 terms are going to be representing this one surface integral. Now I will go back one more level and I will say, in my original equation I have this surface integral is going to be replaced by those 3 terms which we just talked about, plus this term which became these 2 terms, of which this term we wrote as one simple expression in here. Okay. So there is a whole set of equations. We will put all of them together and write it once, the full equation in volume integral form. I will fold and write here. I want to give some gap a little bit here, it helps after some time. This whole thing is one equation, okay, of which we know that this is your del p term that is coming from tau tensor dot n ds integral converted to volume integral. These are the 3 terms which we just talked about, of which 2 of them are just sitting here directly above. This is the first unsteady term. Now the time derivative is operating on individual terms instead of what we had before as a group. Dou by dou t of rho u together we had it is operating on individual. That is the whole thing we have. Now we want to group it in a nice fashion. We want to say I will group these 3 terms, that is why I wanted that gap here. I want to group these terms, all of them have a u vector multiplied by something. Now I will group them that way, just take that bracket alone, it will look like u vector multiplied by it will look like this. Now this is just your mass equation which we just derived last class. Okay. This u vector multiplied by mass equation, and if I say my flow is obeying mass equation, this will automatically be 0. Okay. So my expression can be simplified to just this term plus 0 plus these 2 terms. That is what we are going to use from now on. Okay. And now we will say again whatever logic we used last time, we said the integral should be valid for any small volume dV. So ideally my floor bracket inside the integral, that must be equal to 0. So we get to the differential form of the expression. Remember the integral form which we started with and the differential form, we will use all of them. So what is the integral form? We will go back here. This original thing is my integral form. Integral form is this whole expression, of which you should remember this form along with the change to derivative form which will be in here, this whole expression here. Up to here we want to keep both the expressions, we will use one or the other depending on the situation, whichever is convenient. Okay. So I will get a final expression, I will write it in the next board. This happens to be your differential form of full momentum equation. Of course, it is 3 equations together, I have to put this vector symbol here on top. It is actually 3 equations together. If I look at it, there is x component, one full equation is there, y component there is a full equation, z component there is a full equation. This grad p is going to have 3 components in there. So each of them will go to one particular equation specifically. If you want to think about it, dou p by dou x is going to be in x momentum equation, dou p by dou z will be in z momentum equation or the w momentum equation, whichever way you look. Okay. Now is this expression for compressible or incompressible flow?
Incompressible.
Why is it incompressible flow?
Oh yeah, compressible.
He already changed the answer. So he says it is compressible flow. Why is it valid for compressible flow?
Del dot u equals to 0, that means it is incompressible.
Del dot u equal to 0 we used somewhere. Where did you use it? Are you going to say it here? This is a mass equation. We said this whole term is equal to 0 in mass equation. That is what we said, right? So if we look at the original expression for momentum equation, if I do not use this simplification, the actual momentum equation happens to be this, whatever is inside this floor bracket equal to 0, that is your original momentum equation. If I look at it that way, I am having this dou rho by dou t term. Okay. So in theory I have to say that density variation is also taken into account in this, except for I am simplifying this expression using mass equation, because mass equation is also satisfied in my flow problem. Mass equation and momentum equation are satisfied. So I will simplify this So, even though I write my expression in this form, it is still valid for compressible flow. Okay. That is the important point you have to remember, it is valid for compressible flows, okay, even though there does not seem to be a direct time variation term for density. Okay. That is the typical thing people use in interviews. They will tell you to write this expression and then they will ask whether it is for compressible flow or incompressible flow, standard trap, right. Just tell you that, do not want to fall in that trap. Okay. Anyways, so now we will move on to conservation of energy. Okay. So, this same thing can be used here, rate of increase in volume V. Okay, I am going to say how much is being collected inside my pocket. We talked about this accumulation term, that is going to be there. Okay. Plus the net outflux. I am writing a little less in here. Ideally, I would write net outflux, the net rate of outflux of energy across surface S. All that I would write here really. I am just writing here net outflux across S. Okay. That is how much am I keeping inside, how much am I sending outward, out of my control surface. Those are the two things. Okay. And then other forms of work done by me on the surroundings, that is the next thing, remaining thing. I will just call it W out for simplicity. Ideally, I would write net rate of work done on the surroundings, that is what I would write here ideally. Okay. All this, let us say, are going out from the system. Okay. Now, what is the input? The heat transfer in, that is the only thing, or some other source term that is producing energy inside. Okay. All these are just rate of increase of energy inside the volume, but what increased it? Everything seems to be using of energies for something. What increased the energy? That is your net influx. I will just call this your, actually it is not just Q in, this is not just W out. Ideally, I would write rate of. Okay, we are thinking about time rate of change of quantities. In this case, it is energy equation. So, it is energy quantities, energy. Okay. Now, let us look at a Q in term. What is the net rate of Q in? What are the various ways by which I can give energy into my control volume? Q is heat transfer. So, what are all the various things that is possible? Some kind of, what is the process? We are looking for the process, not heat exchanger. Yes, that is a mechanism by which I can give heat to gas. Yes. Convection, not really convection. It is not convection. We are looking for conduction. Conduction, basically heat is being conducted because the walls are hot and the gas is cold, something like that. So, there is heat transport due to temperature gradient. What law governs this? Law of conduction, named after who? Fourier. Okay. Fourier's law of heat conduction. Okay. It should have been sometime in high school, you are given this, or first year at least in engineering. So, now I want to look at how much is the net heat into my volume. So, I have to look at my control volume and say every surface, this is my surface of my control volume S, and I am going to say every surface there is some amount of heat coming in, which means temperature here is higher than temperature here. What is the direction of my temperature gradient? Gradient has a direction, by the way. What will be the direction of my temperature gradient? Del T has a direction. it is in the direction of nobody ever thought about del, let us say del p we looked at just now, momentum equation. What is the direction of del p? Normal to isosurface, okay. So, let us use that terminology. I do not know whether it will work very well. Let us say I have my space x y coordinate system and I am looking at some random gas volume and I have some pressure distribution. Let us say wherever I put lot of dots, pressure is high there, something like that. Pressure is high here, low here. If I take a gradient over this volume here, let us say, if I take grad p, del p, this happens to be a vector, it will have one direction finally, because it is a vector, it has to have a particular direction. What will that direction be? It will be towards the highest change. Okay. Gradient vector gives you the direction of highest change at that point. Whichever direction pressure is changing the highest, it will be putting that direction for you, which is in a way equivalent to what he was saying, it is perpendicular to the isosurface. Perpendicular to that, there will be a line where I can tell pressure is almost the same. I will get to that, that is your isosurface. Okay. But I can have a crazy situation in my flow field where pressure is very high in this annulus, then pressure gradient will be this way here, this way here, this way here, this way here, like that, but still isosurface is still present. Okay. Depending on the resolution, you will see different things. Am I interested in such small differences in distances? If that is the case, then we will see such effects. If I say I am interested in my minimum delta x happens to be this big block, there is no pressure variation for me. I will just take one average pressure for this. Okay. Of course, engineering problems we always will say I am interested in lengths of the order of something, let us say 1 centimeter. Lengths of the order of 1 microns are not useful for me. So, like that we will set our own limits. Depending on the problem, it may change. If it is flow over an aircraft, then I am not bothered about lengths of less than 1 centimeter probably. Okay. If it is flow over my hand, then I may be interested in lengths of the order of 1 millimeter, but not anything lesser. If it is flow over this chalk, probably I am interested in less than 0.1 millimeter or so, because the overall size itself is somewhat small. The overall size itself is roughly 10 mm or something. So, we may be interested in something much more finer, that can also happen. Depending on the problem, you may want to resolve more, that is for people who want to go computational more, others it does not matter so much. Okay. But in any case, grad p you should know is going to be perpendicular to the isosurface, perfect mathematical explanation. Okay. But the actual way we want to think about it, it will point towards the maximum change direction, it will go towards change in the upper direction, it will go from low pressure to high pressure direction, that will be the direction. Okay. That is the way it will be. Now, same thing for temperature, we wanted temperature gradient so that we will have heat conduction, that is what we were looking for. Okay. Now, if I say my normal vector is like this and my q vector, the heat flux vector, is like this, okay, then if I put q dot n, that will have a negative sign, because n vector is like this, q vector is like this, okay, and you will get q dot n will be a negative sign. We want to cancel that because we want to say the q is positive, this q corresponds to positive. So, I have to say my q in, I will put a dot saying it is rate of, I do not want to go and write every time rate of q in, I will just put a dot on top and say that is time rate of change of q in. Okay. Now, I will write this as minus integral over the surface q dot n ds. Okay. Now, what is this q? That is where your Fourier's law comes in. Conduction coefficient times del T. Okay, this is your Fourier's law of heat conduction. Now, I did this gradient of pressure now. Now, gradient of temperature, what does this say? If I go back to this picture, I am saying heat is going this way in, which means this is higher temperature, this is lower temperature, right. So, my grad T will look going outward, but we already defined it to be going inward. So, there has to be a minus sign. That is one way of looking at it. Okay. We just have to be consistent with why we put this minus, why we put that minus. They are two different minus signs, they are going to cancel each other's one. If I substitute this q inside here, that will cancel that minus sign. Okay. We will keep it this way. I will use this form sometimes, I will use this only once. Anyways, finally, we will just say q equal to 0 overall, that is also there. Okay. By the way, the q in need not be always through conduction. What are the other possibilities of giving heat to a volume of gas? Radiation, another possibility. Anything else? Convection will not be working. Conduction is the physical process, convection is the gas molecule. Let us say I have a hot plate, the gas molecule here will come take the heat by conduction and then it moves away. Some other gas comes here, takes the heat and it moves away. That whole process is what people call convection. Engineering wise it is useful. Okay. They will just define one coefficient of heat convection and problem can be solved faster. So, they have a separate thing called convection. Really it is just conduction with flow, that is what is convection, it is not anything special. Okay. So, we will not go into that, I am just going to say there is no separate convection term, that is why I wanted to introduce this. Okay. So, there is only conduction term, there could be radiation term. Other than that, there could be one more thing, chemical reaction. Chemical reaction can be exothermic, producing heat, or endothermic, it can be q in negative, it may be taking away heat, it could be q out from the volume, that could also be there. I could have chemical reactions, but currently in our gas dynamics we are simple enough flow system, we will say no chemical reactions, no radiation. Okay. But they are just approximations. I could have a case where it matters. Okay. This is just one term, we have just written that last term in this 4 term expression. Now, we will go and look at the rate of energy accumulation, that is the easiest term, time rate of change of stuff. Okay. This is E is internal energy per unit mass, we already had this convention, and this is kinetic energy per unit mass. This is the total energy of the gas per unit mass, this is the gas's energy and this is the flow energy all together. This is all per mass multiplied by density will make it the whole energy per volume into small volume will mean that small box how much energy am I having, integral over the whole volume, that will be the net energy I have inside my control volume, time rate of change of that. This is your the first term, rate of increase in inside the volume, rate of increase of energy content inside the volume, that is this term. Okay. This is one term. Now, the next term is energy outflux, that is this net outflux across S. What outflux? Energy outflux, rate of energy going out across the surface. I have to say net outflux. Okay. similar to all the other terms we did for outflux. It will be u dot n times ds multiplied by that quantity. That quantity happens to be energy per unit volume rho times E plus u square by 2. That is the whole quantity we are talking about. We get to this form. Now, the only term left in this equation, we have an expression for this, that is here, we have an expression for this, that is out here. Then the next thing is this right hand side, which is what is the first thing we did, that is this expression. Now, only thing left is this rate of work out. Okay. Now, rate of work out, what are all the various mechanisms by which my fluid can do work on something around, something surroundings? Turbine work, yes, that is a possibility. That is called the shaft work typically. Yes, that is a possibility. Anything else? Pressure doing what? PdV related work, okay, but it is flow. We want to find rate of work done. How do you find rate of work done? I want watts as the units. High school physics, I am pushing a block of metal. What is the net work done? What is the rate of work done? Force into displacement gives you the work, not the rate of work. Force into velocity, but they are both vectors. They are both vectors. So, what should I do? Vectors cannot be generally multiplied. Should be dot product. Okay, you have to know which one, because we are looking for energy which is a scalar, not a vector. Okay, that is one simple way of looking at it. In continuum mechanics, if you give this answer, they will not accept it. You have to give more logical answer for that. Okay. But in here we can give this answer, that is okay. We will say we are looking for a scalar. How to get a scalar from two vectors? Dot product, easy answer. Okay. That is enough for us. So, what is my force really? My force happens to be this stress times ds. Okay. Now, I have to multiply this with velocity along a particular direction. So, I have to dot it with my velocity. This is my rate of work done. Okay. This is my overall term. Now, I have to be careful about this. Why? Because I want to put a minus sign in front. Okay. So, if I have stress, okay, say I am a fluid element and I am moving forward, but the next fluid element is not moving, what will we feel? There is a velocity gradient, so I have to pull that person along. The next fluid element I have to pull along, which means I am applying force this way and I am moving this way. What is the actual force applied on me by the surroundings? It should be the opposite direction, right, because the next fluid element is slowing me down. Okay. I am doing work against that force. Okay. That is the correct way to look at it. You have to think about it and then come up with your own explanation for it finally. Okay. I will tell you this particular way of looking at it, but you may have some other version of it. You can think about it in whichever way you feel like. I will just tell you shear force. It need not be just shear force, we will look at normal force also after this. But shear force is what is the example I gave you right now. Okay. I could go for normal force also, we will go for normal force after this. Okay. I am going to have this particular force which is minus, this is my W dot out. Again I am going to say net rate of work done on the surroundings is what you are looking at. Okay. We will get to this point. So, now again I will write this stress tensor in diagonal and off diagonal terms separately. Okay. Then I can write this expression as tau shear dot u ds. Okay. I missed a equal to sign here, which I do not think is a serious trouble. I missed this equal to sign before. Okay. and then I have to use the correct sign again here, n dot u, right. Here the negative sign is automatically taken into account. Okay. You guys should think about it again, I would say. Now I have this everywhere ds, so all I have to do is integral over all the surface to get my full force, not just full force, full rate of work done on the surroundings. That is what I need to do finally. So I have to just put integral over this over the whole surface. That is what I need to do for both the terms, integral over the whole surface. Now I have taken into account all the terms, all I have to do is just look at the whole expression. The whole expression is not very difficult to write, but anyway I will go to the next section. We have not converted the surface integral to volume integrals, okay, and we will write it without the conversion, remember that form, and then we will convert it, and then the whole volume integral we will just say all the integrand, the inside the integral should be 0, we will tell that also, and then we will remember the differential form, we will keep both the forms. So I will write both. The first one just the whole term, I am going to fold the equation. In case there is shaft work, I will just write this immediately after this point, I will say this is equal to 0 in my problem. Okay. In case there is other forms of workout, then I will keep that. This whole thing is the left hand side. Now that is going to be equal to the remaining terms again. I wrote this term, if I want I can even write chemical reaction here. I just said it is Q in rate of heat in through radiation, and we will again say we will make it equal to 0 in our problem. Same thing as shaft work, we will again say it is equal to 0 and we will not ever consider that. Now of course I can write this in terms of gradient in T using Fourier's law. If I use Fourier's law, this will become just this one term I will write separately here. This is integral over a surface which I missed here, integral over the surface there. Okay. Now I can write this as integral over the volume this is the first change. Now I will use my heat conduction law here, and I should have minus sign here. Okay. Now that will become this term. Of course I will just tell you that this is a possibility, we will not most likely use this, we will use only bulk quantities, we will not go for at a point what is the temperature, what is the next temperature point nearby, and find out the gradient. We will never do that in our simple gas dynamics world. Okay. It is needed when we want to think about how much is the heat conduction across a shock, which we will never go to in our course here. Okay. For now we are in simple world. Now we just want to go write this in terms of everything in terms of volume integral, which is not very difficult to do. Like we did this before, this can be rewritten in terms of del p dot u kind of term. Okay. Like that you can write this term also, there will be a grad of this whole term, it will come up. Okay. We will just write the final form, I will not worry about how you got to this. We have the same method used in mass equation, okay. It will look the same. So I will just write the final form here, which will be, and I am removing the integral and just integral over the volume is for whole thing, and I will just say that whatever is inside the integral must be 0. I will just write that form. We will leave it in this form. Actually I just told that it is a grad somewhere here in this term. I just told when we make it a volume integral just a few minutes back, I told it is going to become grad p. It will not be grad p because there is a dot u here, it will just become del dot pu, it will become this term. Okay. All the other terms are similar to what you did before in mass equation, this one term alone is new. Okay. And then we get to this form. This is your energy equation, energy conservation equation in differential form. Okay. We will keep all these forms. Now we are at a point where we have all the governing equations for the flow. Along with this, we should keep the equation for entropy, that is T ds equal to dH minus V dP. We have to keep that form, or du plus P dV, not du, for you it will be dE. Internal energy, change in internal energy plus P dV, that form, and P equal to rho RT, gaseous state equation. So ideally we have 5 equations. Okay. We will look at what happens when there are 5 equations. How many variables are there? There are 5 equations. How many variables are there? What are the 5 variables we have? Velocity, okay. Volume, not really, because it is all differential equation, it is at a point, there is no volume for your fluid element, it is point. Pressure, temperature, density, velocity, okay. Internal energy is just temperature. Enthalpy is still temperature, Cp times temperature. Okay, we will think about this, we will get back to this next time. There is still one more variable which we just missed. Anyways, so next class onwards we will get into actual gas dynamics. We have just laid the foundation out. Okay, we know thermodynamics very well, now we know we have used mechanics. Next class onwards we will just start solving problems of different types in gas dynamics. See you guys next time.